Now, example, a steel rod of 1 meter long, which is also equivalent to 1000 millimeter long. It has a cross section of 20 mm by 20 mm. You can convert this to 0.02 meter by 0.02 meter. So when you find out the cross-sectional area, okay, you can actually have in terms of mm square or in terms of meter square. So in terms of mm square, you just take 20 times 20. In terms of meter square, okay, it is better for you to convert this to meter and this to meter, so that you have meter square when you find out the area. Why you need to do so? Because the Young's modulus or the modulus of elasticity here is given as 200 gigapascal. So when you look at the unit measurement here, it's in gigapascal, which is also equivalent to giganewton per meter square. So it is in terms of meter square. So that is why it is better for us to find out the cross-sectional area from the beginning itself in terms of meter square. Okay, so the bar is subjected to a tensile force of 40 kilonewton. Okay, so this is the force, and then the question asks us to find the elongation of the rod. Elongation here means extension or the increase in length. Now, if the modulus of elasticity or the Young's modulus given is 200 gigapascal. So I have the diagram here showing you all the measurements here are in millimeter. So you can actually redraw this diagram and put it in terms of meter. It's up to you. Okay, so you can have 0.02 meter, 0.02 meter, and 1 meter long. This is a square bar, and it is subjected to a tensile force or a pulling force of 40 kilonewton. Okay, so here are the steps that you follow in order to solve the problem. Okay, so the first step, find the cross-sectional area of the rod. That is the first thing you have to do. Make sure you write down everything, because I want things to be in steps. Okay, so that is why I give you the hints and the step here in how are you going to solve the problem by steps. Okay, so first step is find the cross-sectional area. So what you need to do is first write down the formula for the area. Okay, the formula for the area, okay, which is the width multiplied by the thickness, or you can take this as breadth multiplied by breadth, or width times width, since they are the same. So you need to write down the formula first. So the formula, you can put A, the uppercase letter A, equals to width times width. Okay, then substitute in the value 0.02 times 0.02. Then find out A is equals to something in square. Okay, so that is the first step. Then the second step, you have to find the stress induced in the rod. So what you need to do is, again, write down the formula first. Write down the formula first. Don't put in the value first. I want you to write down the formula first, because this is the basic of this subject. So what I want you to do is do everything step by step. Okay, then later on when we go more in depth, okay, you can cut short all the steps. Okay, but at the beginning, please learn, okay, doing your stuff step by step. So first thing is write down the formula for the stress. Okay, the stress formula, that is sigma, that is the symbol for stress, sigma, okay, which represents the direct stress, and it is equals to force over area. So you can write down the formula, sigma equals to F over A. Okay, where the F represents the force, the A represents the area. So you will be able to find out the direct stress. Remember, the area that you take, the area that you consider, it has to be this one. Okay, shaded in pink color. Okay, Why you choose this area? Because it is perpendicular or it is being 90 degrees to the line of action of this force here. This is the line of action, horizontal, through the axis of the square bar. So this area here, okay, is the area that you should consider. So the force, 40 kilonewton, that means you take 40 times 10 to the power of 3 divided by this area. So you will be able to find out the sigma equals to something in Newton per meter square. Okay. Then the third step, calculate the strain that is induced based on the definition of Young's modulus. So again, you have to write down the formula for Young's modulus, that is uppercase letter E is equals to sigma over epsilon. Epsilon is the symbol that we use for direct strain. Sigma is the symbol that we use for direct stress. The uppercase letter E is the symbol that we use for the Young's modulus. So once you have written that, then now your epsilon becomes your subject. So bring the epsilon to the left-hand side, and it is equals to direct stress sigma over Young's modulus E. Okay, then substitute your stress, substitute your Young's modulus. Remember, your Young's modulus is in giga, so times 10 to the power of 9. Excuse. Fourth step, once you have found out the strain, now we know that the definition of strain okay, then write down the formula epsilon equals to delta L, that means the change in length, over original length, that means divided by L. So once you have written down the formula, now the delta L now becomes your subject, because the question asks us to find the elongation or the changes in length. So changes in length, that is delta L, will becomes your subject. So bring your subject over to the left-hand side. That means we write your subject on the left-hand side, and equals to epsilon, that is the direct strain, times the original length. Then once you have done that, substitute in the values in the next line, then find out the direct strain. Okay, so these are the steps I have here. So you just take a look. So first thing is cross-sectional area of the bar, the square bar. Okay, it's not a rod, the square bar. So the area should be equals to width times width. So the width is 0.02. The thickness or the width, the next one is also 0.02. So put in, if you want it to be in millimeter, so you can straight away put 20 by 20. So you can find out the area of 400 mm square. But in this 400 mm square, later on, you have to convert to meter square. So remember your unit conversion, mm square to meter square. So you have to remember 1 mm, excuse, 1 mm is 10 equals to 10 to the power of negative 3 meter. excuse. 1 millimeter is equals to 10 to the power, 1 millimeter is equals to 10 to the power of negative 3 meter. So since this is square, so your 1 square mm square is equals to 10 power negative 3 power 2 meter square. So you got 10 to the power of negative 6. So if this is converted to meter square, so it should be 400 times 10 to the power of negative 6 meter square. Okay, then the next step, the stress. Okay, so write the formula first. Sigma represents the direct stress, the force F, and the cross-sectional area. Remember, the area and the force must be being perpendicular to each other, because you are looking at direct stress, not shear stress. Shear stress is different, direct stress. So putting your force of 40 kilonewton, so that is why you times with 10 to the power of 3, divided by the area which you have found, 400 by times 10 to the power of negative 6. Then you can find out your direct stress, which is 100 times 10 to the power of 6 Newton per meter square. Okay, or you can write it as 10 power of 6 is actually mega. So you can write it as mega Newton per meter square as well. Okay. Then the next step, okay, Young's modulus. So you have to know what is the formula for Young's modulus. That is the uppercase letter E. The E symbol stands for Young's modulus, which is equals to direct stress over direct strain. Now, since we are finding out the elongation, that means the change in length of the square bar. So this epsilon here consists actually the delta L over the original L. So if you are able to find out the epsilon, you will be able to find out the change in length. So your epsilon will become the subject. So bring the epsilon over to the left and bring your Young's modulus E to the right as the denominator. So you have this. So put in the value of stress. Remember, this is mega, so you have to put 10 power 6. And your E is 200 gigapascal just now, right? Which is also equal to 200 giganewton per meter squared. So remember, you have to times with 10 to the power of 9. And double check both of these, okay, units here, okay, they have in terms of meter. So everything settle, put in the values, find out the direct strain, okay, in this form, or you can write it down into this form. Then for the elongation, then you have to know the definition of the direct strain. The definition of direct strain is delta L over original length L. So what we need is this delta L here, that is the elongation. So change this to be the subject. So bring it to the left, okay, or rewrite this so that this is on the left-hand side and epsilon times original length to be on the right-hand side like this. Okay, so put in the value of epsilon. Now, remember direct strain here is unitless, without any units. Why without any units? Your delta L, let's say, is in meter. Your original length, let's say, also in meter. So meter over meter, so you can strike it off. So epsilon, that is the direct strain, is actually a ratio between the changes in dimensions over the original dimension of the object. Okay, so if you take the same unit measurement for both the numerator and the denominator, this epsilon here shouldn't have any units. And most of the time, it must be less than 1. It always have to be less than 1. Because if it is greater than 1, that means your changes in length is more than your original length, which cannot be tolerated. Okay, any object that undergoes such a deformation, that means it will extend more than the original dimension of the object. That means whatever you design using this material, it will fail, it will break, or it will collapse. So make sure your epsilon is always less than 1 and without any units. Okay, so from here you put in your your epsilon, your direct strain, and then your original length, that is 1 meter. Use 1 meter, okay, so that you get your change in length in meter also. If you use your length to be in millimeter, you will get your changes in length also in millimeter. So put in the values. So you'll find that it is 0.005 meter. Or if you want to change it to mm, you can do so. So multiply by 1000, so it becomes 0.5 mm. Okay, that's for this example.